Okay, so one person wants to go over the last couple Chapter 18 practice problems. We can do that. And then someone wanted to go over some of the practice problems from the practice final. So we can also definitely go over that since it's already been turned in. All that lovely jazz. So let's start with Chapter 18. And let's go all the way down here. And I think you said last two. So yes, we can go over those ones. And if you guys want any more from this packet, just let me know, as always. So for...
Rosemary?
Yes, what's up?
Sorry to interrupt. It's not this packet. He has two on Canvas. Like, one of them is like the answer sheet, like the answer document, but it has like additional questions on it, which I thought was weird, but it's the last two in that packet, if that makes sense.
Yes, it does. I know he had that for some chapters. I just didn't realize this was one of them. So thank you for letting me know. Where in the world are all of his practice problems? There we are. So this one?
Yeah, I believe it's that one. And then it's like the last two, I think.
Okay, cool.
Okay, thank you.
You're very welcome. I am going to open this and I am going to really hope that it works. It's not going to. Cool. So I'm just going to screenshot these real quick. Okay. Okay, cool. I know this is so annoying, but I don't know why my iPad can't comprehend PDFs. Okay, so for this first one, we are going to go ahead Okay, this works. So if he gives you this set of reagents, right, we don't know what Y is yet, but we kind of know what this will do, given the context that it's chapter 18, and we have a negative charge and some other random reagent. So what do you guys think that this guy could do, possibly? I phrased that kind of weird. Based on what we've done in chapter 18, what do you guys think this negatively charged reagent will do? And then I know that there's a big question in the comment. I'm going to read that when we're done with this one. And so, yes, it could definitely take an alpha hydrogen. And so before I draw that out, what functional group is this and this? Ester, exactly. We could also call it the malonic ester, I believe. Oh my gosh, could you not? That'd be cool. Thank you. So it's going to look like so. And we know that we only have one alpha hydrogen, and that's going to be this guy right here. So this negative charge is going to steal that hydrogen, give those electrons back to the carbon. Alrighty, so now that we have that negative charge, what would be the next step usually? An SN2 like reaction, exactly, and you would end up adding what kind of group to our carbon? An alkyl group, exactly. So in this case, we don't know what Y is, but we know that it's going to be some kind of alkyl group. So if we zoom out, they actually gave us the answer. And so given this, we can figure out what y is, and then what z is going to be, and then this whole thing. Right? So remind me, what are these reagents going to do? It's going to be 2 different steps. What are those 2 steps going to be? Hydrolysis and decarboxylation. Exactly. So all right. So in a decarboxylation, we end up, I'm sorry, I don't know what happened to you guys. You disappeared. There you are. Okay. In a decarboxylation, you do end up making a double bond, right? But is this double bond going to be caused by the decarboxylation, or does that come from our alkylation? The alkylation, exactly, because if it was the double bond from the decarboxylation, what 2 carbons would it be in between? And I know that's a really weird way to ask that question, but I want to see if you guys can think about it. So the double bond that's formed from the decarboxylation would be between the alpha carbon and the carbonyl carbon. Exactly. So for that reason, we know that this is going to be Y. Some halogen. And then once we add that to our chain, I'm going to rotate it a little bit just so it's kind of not as ugly as it was before. Ta-da! So at this point, what did we make? Like, are we at our final product? Are we at, whatever? What would we call this product? That's actually kind of a silly way to ask that. So at this point, we made Z. And so in this question, that's all they're asking for. So which of these matches what we just drew? And yes, Ronald, I can do that right now. So while you guys take a look at that and let me know which one of the answer choices matches what we just drew in blue, I have to go ahead and send an email super quick. Okay, I just sent it to you, Ronald. Let me know if there's anything else I can do. Sorry about the mishap. Okay, so you guys are exactly right. So number 2, aka B, would be the correct answer in this question, because we're not looking for the final product. We're looking for the intermediate after we perform the alkylation. Any questions? Thank you, Ronald. Bye-bye. Okay, so I'm going to go back and read the other question that I got while you guys look at this answer. Okay, so this is actually a really great question. So the person asked, at the end of the acetoacetic ester synthesis, they form the enol form. Should we know the mechanism of tautomerization back to the keto form? I think it may be different than how we learned for tautomerization of ketone to enol. So you're right, it would be slightly different. But all you need to know, like, no, it's okay. I won't draw out the whole thing. But all you really need to know is that you're going to make something like this and whatever this R group is going to be. Or in the case of the malonic ester synthesis, you're going to make something like this. And just know the basis of that tautomerization is going to be taking this hydrogen and moving it to this carbon. And that will look like so. And same exact thing for this one. So you don't need to know the whole exact mechanism. As long as you know this general principle, you should be fine. You're very welcome. Also, hello to the person who just joined. I'm so sorry that you were left out of my email. That was completely my bad. I'm glad you're here now. Okay, so right now we're just going over the last two questions of the chapter 17-18 practice problem set, and then we're going to go on to the extra credit final and go over those since the due date has passed. All right, so let me make this one bigger. Alrighty, so for this one, we are first going to look at what they're giving us, right? So we have an ester. What is this? And yes, Jess, we can definitely go over those two questions. Let's just finish this one first, and then we'll go back. So yes, this is an alkyl halide. And what do we have right here? A base, sweet. So base plus alkyl halide usually means what? Alkylation, exactly. So we're going to do just that. And which hydrogen are we going to steal? The alpha hydrogen, so that would be this one right here. So we're going to take that. And essentially, we replace that hydrogen with what? With the alkyl group, exactly. In this case, they didn't give you a specific one. It just says R. So we're going to go ahead and add our R group right here. So the reason the OET group is here is just because this was an ester. The reason it's here is just what our like base would be. So we're not going to add that to our alpha carbon. We're actually just going to add the R group here. Because remember, we'll get a negative charge here. And then we have our RI. It can attack, kick that off, And so we get this. So great question. They asked, are we always taking an alpha hydrogen in this chapter? Yes, pretty much. So this whole chapter is talking about enolate chemistry, which is just taking the alpha hydrogen. You are very welcome. So for this one, number 1 matches our answer that we drew. So someone asked a really great question. How do we differentiate it from other chapters when we're taking the final? And I'm actually going to show you guys a couple examples on how to differentiate. Most of the time, you're looking for key reagents. So how I would study is I would make a big table of all the reagents in each chapter and then what the final product would be, and then write any special notes that come with that reagent. And then once you do that, you'll be able to see like how they're different. So like how this combined with this is different than this combined with, let's say, H2O, right? Or how if this was a ketone, this reaction would be different. Things like that. And then someone asked, why wouldn't this be considered an acetoacidic ester synthesis? And so 2 reasons. 1, because we only have one ester. In order to do the acetoacidic ester synthesis, you would need a ketone on the other side. Plus, in order for it to be the acetoacidic ester synthesis, you would need this reagent followed by NaOH and water, followed by heat. So you need all 3 of those steps in order to have the acetoacidic ester synthesis. You're welcome. Okay, so I believe someone asked for 74 and 90. So let's go back to those ones. Oh, is that from the other set? Okay. Sure. Maybe it was 73 and 90. Alrighty, so this is very similar to the ones, oh, just kidding. 70 and 92. Okay, so let's do that instead. And then if you guys want, we can come back to these type of questions. Okay, cool. So 70. All right. So first of all, what kind of molecule is this? I'll accept 2 answers. It is a lactone. Awesome. And it is also a cyclic ester. A cyclic ester. Perfect. And I believe someone said it in the chat, but what kind of lactone is this? I want at least one more person to respond. Okay, so we got a couple different answers, so let's actually go through. So the carbon right after the carbonyl is alpha. The next one would be beta. And the next one would be gamma. So we're always going off the highest number or the highest letter, I guess. So this one would be a gamma lactone, aka a cyclic ester. Awesome job. Alrighty, so this is one of those where it's really easy to get tripped up between which chapter we're on. So if he just gave you this with no context of what chapter you're in, one, you see a lactone and you think chapter 17. But let's say you didn't think that, right? You just have an ester with something that looks like that. Is this at all similar to the problem we just did? Well, maybe not how we actually go through it, but like in the way it's set up. Is it at all similar? I kind of think so. I mean, maybe you guys don't see it, but when I look at it, I'm like, oh, okay, we have an alcohol and we have an alpha carbon right here. So why couldn't we do a chapter 18 type reaction, right? Or at least that's what I thought when I was in the class. I was like, oh, why couldn't you do that? So the reason we couldn't do that is actually because what? Because we don't have a strong enough base. Exactly. So we don't have our alkoxide. We actually just have our alcohol. So instead of going through the chapter 18 route, we're going to stay in chapter 17. Awesome. And so in chapter 17, what's the first step going to be in this type of reaction? Yes, so the oxygen here is going to act like a nucleophile. Cool. So what is the leaving group going to be? Someone said leaving. The leaving group's going to leave, and we're going to open up the ring. So yes, this bond is going to... Cool, I outlined the black line with a black pen. So this bond is going to break, and this whole thing becomes the leaving group. And someone made a really good point, which was, by the way, would we consider this reaction to be a transesterification? Let's see what the answer is, and then I want you guys to answer that for me. So, essentially, if we do like the Rosemary Fast method, we identify the nucleophile, we identify the leaving group, and we also kick out a hydrogen. So, let's draw the chain, and let's remember to count our carbons. We're going to have 3. So let's draw a 3. What did I do? 4. 1, 2, 3, 4. I skipped the carbon. So it's so important. All right. 1, 2, 3, 4. So on carbon 1, which is the carbonyl carbon, what else should I draw attached there? Yes. The OCH3. Cool. All right, so on carbon number 4, what do I have to add? The alcohol. Sweet. Okay. Yay! Now, we went from a cyclic ester to a linear ester. So we went from an ester to an ester, right? So based on the rules that I gave you, is this considered a transesterification? Yes, absolutely. So awesome. I'm really glad you caught that. And yes, you are correct. So guys, remind me, or which one of these answers makes the most sense, I should say. B, correct. All right. So before we go on to the next one, we know that a couple of these would never happen. They kind of just look ridiculous, right? So this one right here is one of those, because what in the world even happened, right? It's like they tried to do an acetal-ketol reaction, but they forgot there was an ester right here, and just really weird things started happening. That's a terrible answer. This one can almost trick you because that side is correct, but they added a second methyl group here, so we made an ether instead of an alcohol. That's really weird. We don't want that. This one, again, can almost trick you because one side is correct, but where did they get this thing from? No, we don't want that. Ew. And here, it's just a double whammy. It's like they went opposite and they added our OH here and they added our OME here. So that's all flip-flopped and backwards. We don't like that. Ew. So are we happy with answer choice B? So great question. It was, how was the H on CH3OH removed without a catalyst in this reaction? So let's look at it real quick. Why does it do that? I don't understand. All right. So in the first step, we're actually going to go ahead and do this. And so we end up protonating the carbonyl. We get a plus charge. And so at this point, we have this negative charge right here. The negative charge can then attack, kick up these electrons, right? We still have the plus charge. We don't have the double bond anymore. And we have this, right? So at this point, wow, I'm so silly. That doesn't have a charge. So at this point, what do we want to do in order to kick off the leaving group? Reform the double bond and open up the ring. Sweet. So these electrons come down, kick open that ring. I'm so sorry. So yeah, let's just pretend that's not happening. So we reform the double bond and we still have the plus charge because we have the hydrogen still attached. And now we're going to make our 4-membered straight chain, right? And so now we actually have O- here. And so we're going to do an intramolecular proton transfer to move the hydrogen around. So that's how we would navigate that hydrogen without a catalyst. Ta-da. And then someone asked, did we have to undergo the first step where the carbonyl oxygen was protonated? I mean, you don't have to, because again, there's a bajillion ways to draw that. You could have just attacked the way it was and then done an intramolecular proton transfer here. But I draw it that way because it's more favorable. You make the electrophile more electrophilic and you make the nucleophile more nucleophilic. So it's kind of like a double whammy. Yeah, so they said they thought that the intramolecular proton transfer would happen from here to here. That is also correct. If you drew it that way, you're correct. It could also happen that way. I just like to do it this way because usually people understand why this attack happens if they see, oh, this has a negative charge and this has a positive charge. And no. So the follow-up question was, we won't be tested on how to do the reaction for the exam. So no, you're not going to be tested on like pushing arrow mechanisms or anything. As long as you can get the right answer, you are good in whatever way you're doing it. You are very welcome. Okay, so the next one we wanted to go over was 92, I believe. Something like that. And 92, yes, okay. So this one we're actually not really going to care about just because it's talking about nitriles. And Dr. West had told Katrina and I that he's not going to really test you on that. And we never really covered it in SI or anything. So we're just going to ignore that one for now. Is chapter 19 on the final? So we emailed Dr. West for a meeting and we never got a response. So for right now, we don't know if chapter 19 is going to be on the final. What I'm thinking is to just send you guys like, because I want to do like a chapter 18 cheat sheet thing like I've been doing for all the other chapters. So I was thinking of just including a chapter 9 quick cheat sheet, not 9, chapter 19 quick cheat sheet with just those 2 reactions, and like everything you would possibly need to know about it, so we don't waste time and stuff. And then follow-up question, it wouldn't be the whole chapter though, right? No, it wouldn't. It would just be the 2 reactions from that chapter, which are the 2 condensations. So yeah. And yeah, on the calendar, one of the days says chapter 18, 19. So that's why I don't know, because usually he says that chapter 19 ends up just being extra credit because he doesn't really get to cover it. So it says in the calendar to do it, but I don't know if he's going to test you on it. Same thing like with nitriles, like that was supposed to be in the stuff, but he told us not to worry about it. And I don't think any of his lectures went over it, and also it wasn't on the practice final, as you guys are saying. So I think it would just be mean if he did that. I don't think he's going to, but I don't want to like lie to you guys and be like, oh, for sure it won't be on the final, and then it ends up there. So I will send you how to do the reaction. I will send you like the step-by-step mechanism and everything. But in my opinion, that would be the last thing that I would study. Because even if it does show up on the exam, it'll be like 1 question versus everything else. So, I hope that makes sense where I'm coming from. Okay, so speaking of the practice final, you guys wanted to spend some time on that, correct? Okay, and then there was another question about like the final. So it was, would you say that watching the lectures again would help? That entirely depends on how you learn, which might not be a very helpful thing to say. But me personally, I like seeing the lecture one time and then just practicing with my notes a couple times. But I know there's people who are like strictly visual and auditory learners, so they like watching the lectures over and over and over again. So if lectures help you, watch them as many times as you can. I would say though, the biggest thing you should be spending your time on is practice problems. Do as many practice problems as you possibly can. So 1, you know what kind of questions he's going to ask you. 2, you kind of know like what he's looking for, because we go over a lot of stuff, but for example, you don't need to know every single arrow, right? You just need to know the final product, and there's a couple really good concept questions there. And also you want to be able to do them fast. So like the practice final, you want to be able to go through all of those questions in like a timely manner and like get it done kind of fast. Yeah, so that's my take on that. I don't know if that answered your question, but okay, cool. So then someone said, could we do 80? So yes. I really love that these are all like out of order and really weird. Just makes my day. Is there an 80 on the other sheet? Yes, we can. Yes. All right. So, rip. Okay. Did it cut off for you guys, or is it just me? It cut out. Okay, let me really quickly go back and share it. Let me know once you guys can see it, please. And then, yeah, someone said, I just realized there's a second practice sheet. Same. I thought they were both the same. Alrighty, so this is number 80 on that sheet. So immediately, what kind of starting material are we dealing with? Yes, an acetoacetic ester. And so what is the more broad name for this? Like this kind of molecule. What is the more umbrella-like name? Yes, exactly. It is a beta keto ester. Could you please just not? Okay. Beta keto ester. Awesome. So if we have an acetoacetic ester or a beta keto ester, we know that this will be the acetoacetic ester synthesis. And from our knowledge of this reaction and from these 3 steps, let's go ahead and kind of label them so we know what we're doing. In the first step, we have base and an alkyl halide. So what is that first step going to be? What kind of reaction? Alkylation, exactly. So this next step has NaOH and H3O+. What's that going to be? I'll accept 2 answers for this one. There's a broad and more specific term. For this step. Hydrolysis, cool. And what's the more broad term? Bless you. Think back to chapter 17 reactions. What were those called? It's okay. So we call them nucleophilic acyl substitutions. Awesome. See, you guys knew it. You just needed a hint. All right. So yes, the next step will be nucleophilic acyl substitutions, aka more specifically a hydrolysis. And so when we have heat, what reaction is that going to be? Decarboxylation, yes. Sweet. And they're nice enough to tell you down here that we get rid of the CO2. Awesome, in case we forget. So we're going to do this kind of in the quicker way that I like to do it in. So we start with the acetoacetic ester and we undergo alkylation, right? And we know that this is our alkyl halide. So we know that in the SN2-like manner, this is going to get kicked off and it's going to be the leaving group. So we're going to attach this R group. And where are we going to attach that? What do you guys think? Where are we going to attach the R group in the alkylation? Yes, so the position between the carbonyls, but remember, wow, excuse me, this is the alpha position. So the carbonyls are beta to one another, but the spot in between them is still the alpha position. So yes, we are going to, honest mistake, I know it happens all the time. So we're going to just go ahead and draw that attached. And the next step, we said we have hydrolysis. So we're going to kick this off as the leaving group. And we're going to replace it with what? OH, exactly. So we get I'm just going to write pH because I don't want to draw it again. So that's a really great question. Someone asked, is this step also a saponification? I'm gonna say no, just because first. Sorry. Actually, no. I'm gonna say no. Just because I believe in order for it to be a saponification, it specifically has to be in base. But I can look into that because I'm not 100% confident. I believe that's the case, though. Alrighty, so in the next step, we do a decarboxylation. And so that one we're actually going to do step by step because that's kind of a new thing. Bear, shut up. Thank you. All right, so in the saponification, or in the decarboxylation, what are we essentially trying to do? Like, what are we trying to kick off? Oh, and then someone asked, how does H3O plus interact with the ester? So basically, H3O plus is just there to be a catalyst. It'll protonate the carbonyl, and then once this comes off, that hydrogen will be used to make this an OH instead of just an O minus floating around. So we got a couple different answers. First thing we're going to do is rotate this. And so now the carbonyl is pointing down, the OH is pointing up, and that's a little bit too close. All right, so what is the point of moving the hydrogen to be in between the two oxygens? What kind of bonding are we going to have? So what was the point of moving this hydrogen here in between these two oxygens? What are we trying to have? Specific kind of bond starts with an H. Hydrogen bonding, exactly. So in the first step of this, we're going to have hydrogen bonding. And so these electrons are going to be used to steal the hydrogen. These electrons are going to be used to create a double bond. Oh, wait, my screen cut out? That's awesome. Cool. Can you guys see it again? Yes? Okay, cool. Alrighty. So then this last bond has to be broken, and we send those electrons over here to make a double bond. And so we get on one side, we'll have a double bond here, and we have a bond to hydrogen. And here at the end of this double bond, we have our R group. And we also have CO2 hanging out in the corner as our byproduct. Right? And so just before we look at our answer, we can undergo a tautomerization here. And so we can also have this, and now the green hydrogen has moved back down here. So with all of that information, which one of these answer choices makes the most sense? Which one do we like the most? Three. Yes, I also agree. That kind of rhymed. Okay. Ta-da! And the other ones, I was going to go through and say why they're wrong, but they're all just kind of like so wrong that it almost doesn't make sense. Any questions on this one? Comments, concerns? Okay, so I'll give you guys a second and I'll keep this up. So I am so sorry about how much of a mess today's session was. Today's been just a huge mess. But I appreciate you guys for coming and being so great and participating so much. You guys did awesome. I'll stay on here as always for like a minute or two in case you guys have any questions, but I will let you guys go. And yes, there is tutoring next week. They are special hours. I believe it's on Tutor Track. It'll be Tuesday and Wednesday from 11 to 1, I think. And then do you need to still sign up for them? I think that you can just drop in. I think. But I'm not 100% sure because I don't know what they're doing, to be honest. I know they're like putting our links up on the website, so I don't think you need to sign up. But I can look into that and let you guys know. You're very welcome. Okay, so if they're not available, then maybe they are just going to operate as drop-ins. I can see them on my end, though, so that's weird. But I will let you guys know once I know.